This video is going to cover Chapter 2, Section 6, and then this section actually continues into Chapter 2, Section 7, which is rational functions and asymptotes. So we start with what is a rational function. So rational functions are quotients of polynomial functions. This basically means that a rational function can be expressed as a fraction of one function over the other. So both the numerator and the denominator separated out would individually be functions, and then you would write one as one over the other. P and Q are obviously polynomial functions, and Q of x cannot equal 0, because if Q of x equals 0, then the entire thing is undefined. The domain of rational functions is a set of all real numbers, except the x values that make the denominator 0. So just like our old domain rules, anything that's in that denominator, you would set not equal to 0 and solve it to restrict your domain. In addition to that domain restriction, just a quick review of all three. So domains of a function are all real numbers except for one of these three cases. If there's a variable in the denominator, like we just said, where we would set the denominator not equal to 0. If there's a variable under a square root, and in that case we set what's underneath the expression greater than or equal to 0, because we can't square root a negative number. And if there's a variable under square root in the denominator, combination of the two, we change so that whatever's underneath the square root is now greater than 0. So we're obviously going to focus on the ones in which they have a denominator, because those are rational functions. So find the domain of the rational function. I, in this case, ignore the numerator because there's no square root, and I go straight to the denominator. I would say x minus 4 cannot equal 0, and so x cannot equal positive 4. And we write domain in interval notation. So this is from negative infinity up to 4, but not including 4, so it gets a parentheses, union 4 to positive infinity. So that's the same way of saying all real numbers except 4. Now, same set of instructions. Again, no square roots or anything like that. Go straight to my denominator. X squared minus 36 cannot equal 0. And you can either add the 36 and then make sure you square root using the even root property, which means plus and minus, and I'd get x equals, or cannot equal, plus or minus 6. Or I can factor x squared minus 36 cannot equal 0, and I get x plus 6 and x minus 6, because that's the difference of two squares. And so I would split it up and say that x cannot equal negative 6 or positive 6. Whichever way your brain sees it is totally fine. Just make sure that you don't forget the plus or minus on the square root one. So now x can be anything but negative 6 or positive 6, and interval notation that goes from negative infinity to negative 6 can't be negative 6, so it gets the parentheses, union negative 6 to positive 6, because it can be all the numbers in between them, and then 6 to positive infinity. So by putting the the parentheses here and here, we're saying it can't be negative 6, and here, we're saying it can't be positive 6. Now we're using transformations to graph. So if you remember your parent function of your f of x equals 1 over x, this function had asymptotes at y equals 0 and x equals 0, and it got as close to without touching those lines in both the first quadrant and the third quadrant. So when we look at these examples here, if it was inside the function with it, that's a horizontal transformation. This is in the opposite direction you would typically think. This is left 3 places. So now my vertical asymptote is actually running through negative 3. My horizontal is still running through 0, 0. So then I go first quadrant and shifted third quadrant. In the second example, we've got the horizontal shift here, which means right 2 this time. And then you've got your plus 1, which means up 1. So now my vertical asymptote gets shifted to the right 2. And my horizontal asymptote gets shifted up 1. And then it goes top right corner, bottom left corner. All right, so this is again that parent function. In this case, there's a vertical asymptote on the y-axis. So there's my vertical asymptote. I would say that is at x equals 0. So we're eventually going to talk about 3 different types of asymptotes: vertical, horizontal, and slant. This is the first one. So you're going to see, this is just arrow notation. You're going to see some of this in examples in the book. This is just read as x as it approaches a from the right. So if I'm looking at x, I'm going from the right, which means I'd be coming in from this direction at whatever number is happening here. This is x as it approaches a from the left. So now we're talking about x approaching from the left, whatever number this is. This would be your a. This is as x is approaching infinity. So now we're saying that it's moving towards positive infinity. And this is as it's approaching negative infinity, which would be going in the other direction because we're looking at the x values. This is 1 over x squared. So our parent function for 1 over x was top right corner and bottom left corner. This is 1 over x squared. What happens with the squared is that curve that's normally below the x-axis flips to become on top of it, because if they're squared, all the x's that are squared means that all the results are going to be positive numbers. So this is where that little notation comes into play. Basically, if you read this, it says as x is approaching 0 from the left, my function is approaching positive infinity. So as my x is approaching 0 from the left, it's doing this, and then it turns and it's going up to positive infinity. Without bound means it never stops. As x is approaching 0 from the right, f of x is also approaching positive infinity. So now I'm coming in from the right, it's getting closer and closer to 0, and my f of x or my y is getting bigger and heading towards positive infinity. And then the bottom says kind of the reverse. As x is approaching negative infinity without bound, my f of x is getting closer to 0. So as my x is going towards negative infinity, my y is getting closer and closer to 0. And as x is approaching positive infinity, my f of x is approaching 0. So again, as I move towards positive infinity, my y is getting closer and closer to 0. So notice that it never touches that 0 line. It never touches y equals 0, never touches x equals 0. It just gets closer and closer the further you move away. All right, so vertical and horizontal asymptotes. The line x equals a, so notice it's a line, which means it gets an equation as x equals, is a vertical asymptote of the graph of f when f is approaching f of x, is approaching positive infinity or negative infinity. So as my y is getting bigger or my y is getting smaller, it gets closer and closer to that vertical asymptote. And as x is approaching that a, whichever the a value is, either from the right or left. The line y equals b is a horizontal asymptote of the graph when f of x is getting closer to b, or as x is going towards positive infinity or away or negative infinity. So if we go back to those graphs, if I just specifically talk about this one, my vertical asymptote would be here, because as my f of x is approaching positive infinity or negative infinity, if it were going down, then it's getting closer and closer to a, which is my vertical asymptote. The line y equals b is my horizontal asymptote. So as my f of x gets closer and closer to b, my x goes to positive infinity or to negative infinity. In these pictures, you can see examples of graphs with vertical asymptotes with 2, 1, and none. So if you look at that first one, you actually have 2 vertical asymptotes, one here, one here. And notice that these graphs get close to but don't touch those vertical asymptotes. Here's an example with just one. So you've got one vertical asymptote here. This one's approaching it from the left. This one's approaching it from the right. Again, it never touches those axes. or those asymptotes. This one actually has a hole, which we're going to talk about a little bit later, but that's what a hole looks like. And then this last one has no asymptote. So there's no split in my curve, there's no break. And these are horizontal asymptotes. So you've got one with a horizontal asymptote at the middle. Now notice you can actually go through the horizontal asymptote sometimes, but what happens on the outside is that these points are going to get closer to that horizontal asymptote without touching it. This time, my graph does not cross through the horizontal asymptote. And this time, there is no horizontal asymptote. There's no break in my graph. So just a couple examples of things you might see. Now let's talk about how to find those vertical and horizontal asymptotes. So given your function equals f of x equals n sub x, which just means numerator, and d sub x denominator. My vertical asymptotes occur where the denominator equals 0. So whatever's in the bottom, I would set it equal to 0, and that's where my vertical asymptote occurs. My horizontal asymptote occurs in 3 different cases. So if the degree of the numerator, we're talking highest exponent of the numerator, is less than the highest exponent of the denominator, so n stands for numerator, m denominator. If the degree of the numerator is less than the degree of the denominator, then the graph has a horizontal asymptote at y equals 0. If the degree of the numerator equals the degree of the denominator, then the graph has the horizontal asymptote at y equals the leading coefficient of the numerator over the leading coefficient of the denominator. And as a reminder, leading coefficient is the number on the front of the variable with the highest exponent. And then the last case is if the degree of the numerator is greater than the degree of the denominator, then there's no horizontal asymptote. Okay, so example 3 says find the horizontal and vertical asymptote, if any, of the graph of the relation of the function. So I'm going to start with the vertical asymptote first, because those are less tricky. If you look at A, vertical asymptote comes by simply setting my denominator equal to 0. So we've already worked this out. We know that this is plus and minus 6. My vertical asymptotes are at x equals 6 and x equals negative 6. 2 separate lines, one running through x is positive 6 and one as negative 6. For the horizontal asymptote, you have to first identify the degree of the numerator and the degree of the denominator. In my numerator, x is raised to the first power, and in my denominator, the largest exponent is to the second power. So because the degree of the numerator is less than the degree of the denominator, my horizontal asymptote is y equals 0. I go to B. Start the same way. Vertical asymptotes come from setting my denominator equal to 0. This time I'd get x squared equals 4, and x equals plus and minus the square root of 4, which is 2. So I have 2 vertical asymptotes, x equals negative 2 and x equals positive 2. And then my horizontal asymptotes, the degree of the numerator is 2, the degree of the denominator is also 2. So this is where y equals the leading coefficient of the numerator over the leading coefficient of the denominator. So the leading coefficient of the numerator is the number on the front of the highest exponent, which is 3. The leading coefficient in the denominator is the number on the front of the largest exponent, which in this case would be 1. So my horizontal asymptote is y equals 3 over 1, or y equals 3. Now let's look at C. Vertical asymptote comes from the bottom. X squared equals 1, or plus 1 equals 0. X squared would equal negative 1, and I would square root this. Plus and minus the square root of negative 1. and we're not graphing i's, so there is no vertical asymptote this time. And then my horizontal asymptote, highest degree in my numerator, or highest exponent in my numerator is 1, denominator is 2. When the highest exponent in the top is smaller than the one in the bottom, then I have a horizontal asymptote at y equals 0. Okay, so this one says, consider the function of f of x equals x to the second minus 4 over x minus 2. Because the denominator is 0 when x equals 2, the function's domains is all real numbers except for 2. So again, if we had this set not equal to 0 to find the domain, I would have gotten x is not equal to positive 2. But this time it says, however, there's a reduced form of the equation in which 2 does not cause the denominator to be 0. So if I were to take that initial function and factor my numerator, x squared minus 4 would result in x plus 2 and x minus 2. When that's put over x minus 2, there's actually a way to simplify this function by canceling those out, and I end up with just f of x equals x plus 2. This is actually just a line, because this would be y equals x plus 2. What happens here is I would get this line where it passes through 2 and has a slope of 1. However, because I canceled through something that is initially part of my restricted domain, I have to have a hole at the spot that would have restricted that spot. So if my initial place or my initial function told me that x cannot equal 2, then wherever x does equal 2 on this graph would be a hole. And you would see an empty space there. So the first thing you want to do before you even start to simplify a function is always identify that domain restriction. If there's a restriction before you can cancel things out, that reduces in a hole. Now notice most calculators do not show the hole. So if you were to actually type in your calculator this function, which would be f of x equals, or y equals, x squared minus 4 divided by x minus 2, your graph would appear like this. So I typed it in as x squared minus 4 divided by x minus 2, and notice that it looks like a straight line. You don't see the hole. Holes are one of the things you have to know to check for. So you always want to make sure, 1, you check for the domain from the beginning, and 2, check to see if your function can be simplified. If it can be simplified, you need to, but you also need to remember to account for the restriction on the domain from the very beginning. All right, so now let's put it all together. Talk about how to actually graph these functions from start to finish. Number 1 says determine whether the graph has symmetry. So something like an x squared without an x to the first term is going to have y-axis symmetry. So that's typically when you're going to see something have a curve on the top right and the top left, or on the bottom right and the bottom left. Those would be your 1 over x squared or your negative 1 over x squared, something like that. The other one would be where you have both an x raised to an odd power in the top and the bottom, and this is going to be your origin symmetry. So if I had y equals x over, let's say, x to the third. Now when I change all of these values and I make negative x to the third, it becomes negative x to the third. Every single sign has changed. So remember, that would create origin symmetry, in which it would be something like top right, bottom left. Number 2 says find the y-intercept, if there is one, by evaluating f of 0. So because what's inside the parentheses my x, and my y-intercept I get by plugging 0 in for x, I would plug in 0 for the x and see if there is a y-intercept. Find the x-intercepts by solving the equation of f of x equals 0. Easiest way to do this is just set your numerator equal to 0. Then find what we just talked about in this lesson. The vertical asymptotes, the horizontal asymptotes, graph those, plot your intercepts, and then if you need additional points, plug in points in between each range. Use the information obtained previously from all of these steps to graph the entire function. All right, so let's walk through one from start to finish. This says graph f of x equals 5x over x minus 2 using the 7-step strategy from the previous slide. So I can test for symmetry if I plug in, so if I make it y equals 5 times negative x minus 2, I get negative 5x over negative x minus 2. So it changes almost all the signs. It changes the 5x to negative 5x. It changes the x to negative x, but negative 2 stays the same. So it's not symmetric to the y. And then for the origin symmetry, I would just simply change the y in addition to the x's and see if that changes everything. Again, I've got everything but that negative 2, so it's not symmetric to the origin either. Now start with your intercepts. So my y-intercept, I would plug 0 in for x. I get y equals 5 times 0 over 0 minus 2, and I get 0 over negative 2, or 0. So my y-intercept is 0, 0, which means I should already identify an x-intercept. But I'm going to check to see if there's more. So for my x-intercept, I set my numerator equal to 0, and then divide by 5, and I get x equals 0. So both my x and my y-intercept are 0, 0. Then go through your asymptotes. So my vertical asymptote comes by setting my denominator equal to 0. I get x equals 2. And then my horizontal asymptote, look at both the numerator and the denominator. The degree of both is 1. So this is the scenario where you're dealing the leading coefficient in the numerator, which is 5, over the leading coefficient in the denominator, which is 1. And I get y equals 5. So I have no symmetry. I have both an x and a y-intercept at 0, 0. I have a vertical asymptote at x equals 2 and a horizontal asymptote at y equals 5. Graph as much of this as you can. So intercept at 0, 0. Vertical asymptote at x equals 2. Horizontal asymptote at y equals 5. So because I already have a point down here underneath this curve, I'm pretty sure my graph is going upright and down left. I already have this point, so I don't need to plug another point in there, but you could if you wanted to check it. You do, however, need to plug in a point from this top range and see if your initial assumption's correct. So I'm going to plug in 3 because it's to the right of my vertical asymptote. I would get y equals 5 times 3 over 3 minus 2, which is 15 over 1. So I don't have to plot exactly 15 because it is so high, but I do know that that means that my point is somewhere up here and that my initial assumption is correct, that my graph is going to go in those two areas. So for every vertical asymptote that you end up with, you want to make sure that you have a point to the right and to the left of that vertical asymptote. Sometimes that means that there's 2 vertical asymptotes, and so you've got to get points from 3 ranges, which you'll see in a bit. All right, example 5. So we're graphing f of x equals 2x squared over x squared minus 25, again, using the same 7-step strategy. So let's start with symmetry. This time I have y equals, if I plug in a negative x, both of those values go back positive. And my function goes unchanged, which means there is y-axis symmetry. For my origin symmetry, the right side would be the same, but my left side would have been changed to negative y. That doesn't match the original, nor is every sign opposite. So there's no origin symmetry. Now I go y-intercept. So y equals 2 times 0 squared over 0 squared minus 25. 0 over negative 25, which is 0. X-intercept. Set my numerator equal to 0. So 0 equals 2x squared divided by 2. I get x squared equals 0. X equals 0, but remember that the importance of the fact that there's 2 zeros tells you there's a multiplicity of 2 here that will still impact these types of graphs. Now let's do our asymptotes. So vertical asymptote, denominator equals 0, which means x would equal plus and minus 5. Horizontal asymptote, degree in the top is 2, degree in the bottom is 1. So my vertical asymptote, or my horizontal asymptote, is at y equals leading coefficient in the top, which is 2, over leading coefficient in the bottom, which is 1. Now let's plot what we've got so far. So the only point I have is 0, 0 again. I have a vertical asymptote at both x equals positive 5 and x equals negative 5. And I have a horizontal asymptote at y equals 2. So I know two things about what's happening in the middle. One is that it's bouncing off that 0. 2 is that it's symmetric on both the left and the right side because it's symmetric to my y-axis. So I'm assuming my graph is doing this. And then you'll start to see what's going to happen to the right and the left of this. I've got to figure out by plugging in some points. But I do know because it's symmetric that what's happening on the right is happening on the left. So I'm going to plug in a point to the right of my furthest right vertical asymptote, which is 6. I get 2 times 6 squared over 6 squared minus 25. 2 times 36 over 36 minus 25. And I get 72 over 11. So I know this is 6 and 6/11. That tells me that at 6, I'm up here around there. So now I know the curve in the top corner is doing this. And I can plug in -6 to check it. But because I already did the symmetry, I know that it's happening on this side as well. If you're not great at symmetry, then you can always plug that point in as well. So 2 -6 squared over -6 squared minus 25. I get 2 times 36 again over 36 minus 25, which is 72 over 11. So I get the same point. Now, if you didn't catch your point from the middle being a multiplicity of 0 so that it bounces, you can also take and plug in the points on either side here. So if I were to plug in 1, I would have gotten 2 times 1 squared, which is 2, over 1 minus 25, and I would have gotten 2 over -24, or -1/12. Now I know for sure it's below my graph. That's going to point it this way. And then if I plug in -1, I'm going to get the same point because it's symmetric. I know for sure it's below my graph, which means it goes that way. So there's a lot of different factors going into these type of graphs. You want to go through those steps every time. On a test, it's actually going to say identify domain, identify vertical asymptote, horizontal asymptote, and your intercepts, and then it's going to have you graph it. Okay, so we're going to finish with part 1 here. So this is 2.6 part 1. And then tomorrow we're going to finish talking about slant asymptotes.